So today's Digital Humanities Colloquium series is a presentation by Francois Meyer on Subword segmental neural language generation for Nguni languages. Francois Meyer is a PhD candidate. Actually, I heard he just submitted his thesis and a lecturer in the Department of Computer Science at the University of Cape Town. His PhD research proposed neural network techniques for modeling the agglutinative morphology of Nguni languages in text generation tasks. So language modeling, machine translations, data to text. Previously, he completed his master's in AI at the University of Amsterdam and his undergraduate degrees in computer science and mathematical statistics at Stellenbosch University. So I'm very much looking forward to this presentation. Let me stop my share and then you can take over, Francois.
Okay. Okay, can you see my screen?
At the moment, I only see the Zoom.
Okay.
We tested this beforehand, so I know it can work.
Okay, can you see the presentation now?
That looks better. Yep, that looks good.
Okay. Okay, great. Okay, thank you very much for inviting me, Manu, and it's great to be here. Thanks for coming, everyone. So my talk today will be about some of the research that I've done for my PhD. Like Manu said, I'm at the Computer Science Department at the University of Cape Town. Recently submitted my PhD, and I'm also working as a lecturer in the department. Just to tell you a bit more about our research group. So we are a group at UCT doing work on NLP. We got started a few years ago when Dr. Jan Bass joined the department. He is also my PhD supervisor, so all the work I'll be presenting today was done in collaboration with him. And we do work on text generation, language modeling, machine translation, also supervised and unsupervised linguistic discovery, and focus in terms of application on building datasets and models for low resource South African languages. So if you're interested in this, please visit our group website to see some of our publications and research interests. Okay, so we work squarely in the deep learning side of NLP. So building and developing deep learning models for natural language processing applications. And more specifically, what I'll be talking about today will be about natural language generation. So in NLP, you get different tasks that people work on. And a subgroup of this is related to natural language generation or text generation, which I'll be calling it in this talk. And these are basically tasks where part of the task requires the model to actually generate text, whether it's generating an answer based on a question, generating a summary of a document, or in machine translation, generating a translation based on some input. Okay, so these are text generation tasks. So my talk today, I'll start out basically explaining what subword segmentation is in NLP, kind of one of the building blocks of modern NLP. Then I'll discuss how this relates to text generation for the Nguni languages, which is what kind of the application of my PhD work. And then the approach that we developed for that was called subword segmental modeling. And my talk won't be extremely technical. It will be mostly high level, but then I will go into one particular example of where we did this for machine translation, and then I'll conclude with kind of overarching findings of my research. Okay, so deep learning has kind of taken NLP by storm. So this idea that you have a very large statistical model, which basically can learn everything end to end, which just means that you don't actually give it kind of intermediate linguistic information. You just let the model learn everything that it has to learn for a task from the data itself. This obviously requires a lot of data to actually reach good performance, but it has worked well where you do have a lot of data. So there's been a lot of progress specifically for text generation with chatbots and machine translation. And this is thanks to deep learning. But something that's often ignored is that this is also thanks to subword segmentation. So subword segmentation is kind of one of the workhorses of modern NLP, is often overlooked. But all these models that you see in here, they are not only based on deep learning, but they are also subword level models. Okay, so to explain exactly what subword segmentation means in the deep learning paradigm, I'll use the example of machine translation. So if you're building a deep learning model for machine translation, you will use a dataset that consists of parallel sentences. So for example, if you want to build a model for English to German translation, you have a corpus of millions of sentences in which you have the English sentence and the corresponding German translation. And then you can use deep learning architectures to basically learn this mapping from English to German. And in the past, people use something called LSTMs, but these days the state-of-the-art neural network is a transformer model, which is what ChatGPT is also based on. So you start off with a data set like this, English to German sentences, and then you use what's called the encoder-decoder model. So you just have one subpart of the neural network that encodes the English sentence, and then you have another part, the decoder of the neural network, which generates the German sentence. And this figure or this diagram slightly simplifies what's happening, because in reality, you're actually processing these words not as a sequence of words, but as a sequence of subword tokens. Okay, so the encoder is actually processing the input as a sequence of English subword tokens. So some of the words are actually split into smaller subwords. And then the German sentence would also be generated one subword at a time. Okay, so this is called subword segmentation or subword tokenization. And the question then is, how do you actually get to these subword units? And in modern NLP, it's common to use algorithms that are purely data-driven. Okay, so you're just going to use the data to basically tell you how to tokenize these words. And the idea with this is that ideally you can then just apply it to any data set or any language, and it will kind of adapt to the properties of the language. This is not always the case, though. We'll get to that later. And so what you end up with then is the tokens can either be a subpart of a word, or the largest possible subword token can actually be the whole word itself. So these algorithms can kind of roughly be described as compression algorithms. So they learn like how you can represent a particular corpus with the smallest number of subword units. And this might be useful for some applications, but it's not directly applicable to the task that you actually want to use the model for. For example, machine translation. It has no relation to that objective. So just to give you an idea of how subword tokenization works, I want to show you how probably the most popular approach to tokenization works, which is called byte pair encoding, or BPE. So I'm going to walk you through how it works, and this is really exactly how the algorithm works that probably underlies ChatGPT's subword tokenization, for example. So suppose your entire training corpus is just the sentence, "The cat is in the hat." BPE works by creating an initial vocabulary of all the characters in the corpus, and then it iteratively merges these characters based on frequency of co-occurrence. Okay, so it'll check in this corpus, in "The cat is in the hat," which of these vocabulary items co-occur most often. And first off, it'll see that, okay, A and T co-occur most often, so that then it will join that as a new subword token and add it to the vocabulary. And then it'll do that again, and it'll say, okay, TH is also occurring twice, that's also very common, and then it'll add that to the vocabulary. Okay, so this is frequency based. And it does this iteratively, which means that now it can also look at some of the tokens that it's actually added to the vocabulary. So next up, it'll see that TH and E occurs most often, and it'll add that to the vocabulary as well. And you can do this, you can repeat this process until you reach a vocabulary of whatever size you want. After that, you would then apply this tokenizer, which has now been trained, to your training corpus. So then you have, the cat is in the hat has now been tokenized into subwords. And then if you want to train a deep learning model, you would train it on this sequence of tokens. Okay, so on the sequence of basically pre-tokenized, pre-segmented text. Okay, so that's how BPE works. And BPE is one of a few tokenizers that have kind of come to dominate the field. The other being ULM and also WordPiece. And they work differently than BPE, but what they have in common is that they are all applied during pre-processing. Okay, so they're basically viewed as pre-processing steps. Before you want to train your deep learning model, you run your tokenization algorithm, you apply it to your training data set, to your corpus, you then have your corpus as a sequence of subwords, and then you train your model. Okay, so it's kind of placed and viewed as part of the pre-processing in the NLP pipeline. So what you have today in NLP is not that everything is learned by the model, because one thing that's still actually not learned by the model is the subword segmentation. So as your first step, you would train your segmenter, then in the second step, you would apply it to your data set, and then only would you actually train your model on the segmented text. You have this kind of pipeline set up. So the question is, why would we want to use subwords instead of, for example, words or characters, which was used maybe 10 years ago in machine learning for NLP? So there's a few reasons. One reason is just the fact that morphemes are kind of the smallest units of meaning. So it's useful units of meaning to actually use when you're modeling the language on just a purely semantic level. The other thing is that it will enable models to handle new words. So, for example, if you define to an LLM what the word wug means, you create a new word and you define what wug means, then the model would be able to understand what the plural wugs means or what the word unwuggable means, just because it models these words on a subword level. Okay, so it can combine the morphemes and understand how the meaning then changes. So these are kind of linguistically oriented reasons, but you also have some pretty practical reasons from an engineering standpoint. So it gives you a way to basically handle what's called the out of vocabulary problem. So if your model hasn't seen a word before or it's rarely seen during training, then that might be a problem if you're trying to test the model. So for example, suppose in your training corpus, you have the word cat and you have its plural with the subword, the suffix s. You have dog and dogs, and you only have bird in its singular form. Then if during test time you show the model bird in its plural form, then the model would be able to actually combine it, even though it would be a new word for the model. These won't be new subwords. Okay, so it should be able to learn what these mean and then combine them kind of compositionally. It also can handle misspellings, because if one character or a few characters in the word are misspelled or something is wrong with it, then the rest of the subwords in the word will still be the same. So the model will be able to recover the meaning in some instances. And also just from a computational standpoint, it's much more efficient in terms of the vocabulary that you're going to end up with. Okay, so if you want to actually include all the words in your training corpus in the vocabulary, it's going to explode exponentially. While if you kind of break it up into subwords, as we do here, then this becomes much smaller and it becomes computationally feasible as well. Okay, so this is, like I said, this is kind of taken over all deep learning applications in NLP, not just machine translation. So, for example, large language models like ChatGPT they also process text as a sequence of Subword tokens. So if you enter something into ChatGPT, before it's processed by the language model, some of the words would actually be split into Subword tokens. And the same happens when the model actually generates the response. It will actually generate it as a sequence of subwords and then just kind of show it to you as a sequence of words. So there's actually a website where you can test the ChatGPT tokenizer. I think you can find it by just googling ChatGPT interactive tokenizer, and it shows you how your prompt is actually being tokenized by ChatGPT in the background. Okay, so here you see that I've just entered 2 sentences, and you'll notice that so frequent common English words are not tokenized into subwords, but then less common English words like colloquium, they will be actually split into subwords. And then for a language that's not English, so here's an Afrikaans sentence, you will see that there's more frequently words that are being segmented into subwords. And this is actually something that affects a lot of low resource languages, and there's been some research on that to basically compare how subword tokenization is applied across different languages. And what becomes very evident is that there is a big imbalance between how different languages are represented as subword tokens. So, for example, low resource languages, because they are typically split into more subword tokens, it means that there's actually more compute required to process the sentences in these languages because it's more tokens. And what this means is that actually, if you actually pay per token, which is actually how you would in the case of ChatGPT, because that is how compute is determined, you would be paying more for processing the source language, and while at the same time not actually getting the same quality output as a high resource language like English. Okay, so this affects performance and affects kind of computational efficiency as well for these languages. And this brings us to the topic of my PhD, so specifically how this affects the Nguni languages. So the Nguni languages are obviously low resource languages, but they're also morphologically complex, and that can also actually play a role in how subword tokenization can affect performance for these languages. So the topic of my PhD was basically trying to improve neural network text generation models for the Nguni languages. So, like I said at the start, there's been a lot of progress on text generation using deep learning techniques, but this success is obviously not transferred to most of the world's languages, including the Nguni languages of South Africa. We identified 2 reasons why this is the case. The first is obviously that the Nguni languages are low resource languages. So because of the incredible data requirements of deep learning, we just can't match the performance by just applying the same techniques. So at the moment, if you look at kind of the available resources you need or the data sets that you could use for deep learning to build Nguni NLP models, there are several data sets for natural language understanding. So, for example, bottle speech tagging, named entity recognition. And there are also a lot of data sets for machine translation, which have been released in the past few years. These are very useful. So for these applications, the models are definitely improving a lot. But it's not all positive. So for isiNdebele and Siswati, they remain extremely low resource compared to isiXhosa and isiZulu. So there are very few data sets, and the data sets that are available are often too small to be used by deep learning. And then for natural language generation, so for tasks that require text generation, there really are very few ways of actually evaluating these models. So we don't have a way, for example, to quantify how good is ChatGPT currently for isiZulu or for Siswati, because we don't have, for example, question answering datasets like we have for high resource languages. So besides machine translation, there's very, very few datasets available for text generation tasks. So I did some work as part of an internship during my PhD, where I basically collected a bunch of datasets that are available for the Nguni languages, many of which would be cellular datasets. And so this is kind of a summary of some of what I found. So like I said, for natural language understanding, there is a good amount of data available across different tasks, and the size of these datasets are also mean that you can actually apply some deep learning models to these. But then for natural language generation, there's really very few datasets available. So for isiXhosa, there's a few options, but for the other Nguni languages, what you have is basically any datasets that are big enough to evaluate a pre-trained model. You can't actually train something from scratch on these datasets because they consist of about 150 examples, which is not enough for large scale deep learning. Okay, so that's the first reason why we don't yet have something like a ChatGPT for the Nguni languages. The second reason that we identified, and the reason that we tried to target in my PhD, is the fact that these languages are morphologically complex. Okay, so the subword tokenization of PPE that works so well for English might not be sufficient for the Nguni languages. Okay, so by morphologically complex, I mean, I'm speaking to a lot of linguists here, so usually I have to explain this to a computer science audience. So I'm basically referring to the fact that these languages have complex written word forms, which have to be understood as a sequence of subwords which are kind of concatenated together. And this means that actually modeling these languages at the appropriate subword level is absolutely crucial for Nguni language NLP. So while these kind of heuristic data-driven tokenization methods might be good enough for English with shorter word forms, it might not be the case for languages like the Nguni languages with their agglutinative morphological systems, their conjunctive orthographies, and it can actually hurt performance if the subword tokens are not at the correct level. So, for example, if you're modeling English to isiZulu translation and you have just to use PPE as a subword tokenizer, your model might produce subwords for isiZulu that completely miss the actual level at which you want to model them, kind of breaking morphemes into smaller subwords, which is not as big of a problem with English because, again, you have the shorter word form. So something like PPE is usually applied at the level of words. So that means that you can't really, there's less opportunity for the algorithm to basically split, to add boundaries where you shouldn't at a linguistic level. And in fact, these two issues, so the low resource problem and the morphological complexity, they actually interact and they kind of compound in a way when you're building NLP applications, because because these languages are low resource, it means that the training data sets that you have are going to be small, which means that in your test set, you're always going to have examples of new words or rare words that your model hasn't seen a lot. And this is compounded by the morphological complexity because there are just so many ways that morphemes can combine to form new words. So you already have a much higher proportion of new words in these languages. So this kind of combines to make it an especially difficult problem to build models that work well and handle these new combinations of words in a systematic way. Okay, so the pipeline that I've introduced to you that currently dominates NLP, you're basically segmenting your words as a pre-processing step, which means that by the time you get to step 3, where you actually train your model, your subwords are going to be fixed, And if something goes wrong in your subword segmenter, so if it produces, you lose subwords that are just not good units for actually training a machine learning model, then there's no guarantee that at step 3 your model is actually going to be able to recover from that. Okay, so that could basically disadvantage your model before you even start training, and just make it impossible to overcome that deficit during training, especially because you don't have a lot of training data. So the basic idea of my PhD is to kind of do away with this pipeline and to instead have one model that's going to learn the best way to segment a language into subwords during its training. Okay, so the basic idea behind this was that for the Nguni languages, subword segmentation and good subword units are so important for to optimize modeling performance that we're not going to relegate it to pre-processing. We're actually going to bring it into the modeling itself. Okay, so we're going to have one model that's going to learn during its training how to segment the words into subwords, so that it's not actually fixed. The model can adapt subwords on the fly and find the subword units that work well for its task. So in my PhD, we applied this idea to 3 tasks: language modeling, machine translation, and then data to text generation. So that's where you kind of take structured data as input, for example, tables, and you generate text that summarizes the structured data. But in today's talk, I'm going to focus on how we did this for machine translation specifically. So we call this approach subword segmental machine translation, so SSMT for short. And the basic idea with this is that you want to actually, while the model is learning to be a machine translation model, you're going to let the model learn how to segment subwords, or how to segment words into subwords for the task of machine translation. Okay, so you're making subword segmentation something that the model can learn as opposed to it being fixed. And then the model can actually adjust subword tokenization to optimize its translation performance. And we hypothesize that this would be specifically useful for translating to the Nguni languages. So the standard approach to machine translation, you have your fixed subwords before training. So if this is your subwords, then your model is going to learn to generate the translation one subword at a time. What we do instead is we don't make any assumptions about subword segmentation before training. We just let the model, during its training, consider all the possible ways that a sentence can be and a word can be segmented into subwords. Okay, so in this case, it's predicting all the possible subsequent subwords. And then we have a dynamic programming algorithm, which we use to let the model consider all the possible subword segmentations of a particular word. So, for example, if in the input here, it would one way that it could be segmented is that it actually should be every character by itself. Another way is this alternative, so where some of the characters are joined. Then you have the correct kind of morphological segmentation somewhere in between, but you also have many other possible ways. So this is kind of there's many ways that this could happen, many combinations of subwords for the word Ngiapila. So we have a dynamic program that can do this efficiently, and our model is still a deep learning model. So it's a probabilistic model, so it's going to assign probabilities to each of these subword segmentations. And the idea is that during training, the model will basically learn to assign higher weights, so for example, higher probability to certain subword combinations over other subword combinations. Okay, so in this case, it's learned basically that actually this way of segmenting it is the best way to do it for this task, the task being machine translation. So it's basically learning that this combination of subwords is a useful way to represent this language if I'm training for the task of machine translation. Okay, and we're just letting it learn it from the data, but the difference between our approach and the kind of data-driven approach where you apply during pre-processing is that our approach is linking the data-driven technique to the task. Okay, so to the task of machine translation in this case. So the model can learn subwords as the machine translation task. Okay, so we wanted to see if this would work. Now, this would compare to Subword tokenization, kind of standard machine translation models. So we trained machine translation models to translate from English to 6 different languages. 4 of these were kind of morphologically complex languages, and then we had English to Setswana and Afrikaans as well. Setswana with its disjunctive orthography having simpler word forms, and Afrikaans as well. And as you can see here, it's also, so this is the size of the training data. So we're testing different morphological kind of categories, but also testing languages with different levels of resourceness. So for example, isiXhosa and isiZulu in terms of machine translation have like 8.7 and 3.9 million parallel sentences, which is not too bad. But then something like Kiswati still has a very small machine translation data sets compared to other languages. So we want to see how it works across these different levels of data availability. So we trained, for each of these languages, we trained a number of models. So we trained our own model, the Subword segmental machine translation model. And then we trained 3 models using kind of standard Subword tokenizers. Okay, so BPE I've shown you, and then ULM and DPE are just also applying Subword tokenization during pre-processing. And what we found for English to Setswana and English to Afrikaans translation is that our approach doesn't really help. Okay, so what I'm plotting here is CHRF, which is a way to measure the overlap between the translations that the models actually generate and reference translations, so translations that we know to be correct. So a higher score means more overlap, which indicates better performance. It's not a perfect way to measure translation, but it kind of gets at least at this level of performance, it sees if there's overlap between what's expected and what's actually produced by the models. So for these languages, the morphologically simpler languages, we don't actually see a benefit in using our model. Okay, our model is lagging behind in both cases, kind of the best performing Subword tokenizer. But for morphologically complex languages, so for isiXhosa, isiZulu, and Finnish, we do actually see performance improvements from our model. So these are languages with complex word forms, so it actually helps to have a model that doesn't just treat Subword tokenization as a pre-processing step, but actually optimizes it during training. So what you'll also see here, and this is a problem that's known in the literature, is that among the Subword tokenizers, so among our 3 baselines, sometimes one model does well and achieves the best performance, and sometimes another model does well and achieves the best performance. Okay, so it varies between languages. And this type of inconsistency is something that's been reported. So for different tasks, for different languages, different models do compare differently. And our model kind of overcomes this by optimizing for each language, independently optimizing its performance. Okay, so this is kind of more consistent performance from actually having your model optimize performance for that specific language. So these gains are still is very consistent, but it's relatively small compared to what we get on English to Siswati performance, where we see notable big gains by our model. So English to Siswati is also translating to an agglutinative language, but the difference here is that Siswati is extremely low resource. Okay, so it's trained on a small translation data set. And so this is again where the problem of morphological complexity and data scarcity kind of compound. That is where our model seems to offer the most potential gains. So I think that's where we kind of see our model as being the most promising approach. So besides just testing the actual performance, the machine translation performance, we also wanted to do some analysis to see, okay, we're kind of letting our model learn subwords during training. What actually comes out of this process? What type of subwords is our model actually learning? In particular, is it learning something that resembles morphemes? Is it going to discover morphemes in the process of optimizing machine translation? So we don't actually ever give our model during training access to annotated morphemes. So it's not supervised at all. It's only optimizing machine translation. So it's unsupervised morphological segmentation. But we still want to see, okay, how does it compare to, for example, the Subword tokens that PPE and these kind of pre-processing techniques learn. So, for example, in this case, we have two morphemes that our model has correctly segmented, which here is more than the other tokenizers. So we actually do this across a big data set of morphological annotations. And so this reports morpheme boundary identification, so how many of the actual boundaries it's predicted correctly. And here our model does very well. So outperforms the Subword tokenizers across isiXhosa, isiZulu, and Siswati, which is basically showing that it's learning subwords that resemble morphemes to a larger degree than standard Subword tokenizers. We've also run some experiments on language modeling where we've kind of shown that the degree to which our model's subwords resemble morphemes, it actually correlates to an extent with the performance of the model, indicating that kind of better morphemes or more morpheme-like subwords lead to better downstream performance. So the model, and that's because the model is discovering subword units that are more linguistically accurate. These are the actual units of meaning in the language. Okay, so just to summarize the kind of findings of the translation work, but also more broadly of my PhD research. So we've tried this across a few different tasks now. So we do see that this approach of learning subword segmentation during training consistently improves performance for languages that are morphologically complex. So in cases where kind of the word forms are longer and you have a high morpheme to word ratio, that is where our models do well. It held for other text generation tasks as well, for example, for data to text generation. I'm currently also applying this to kind of larger scale language modeling and prompt-based language modeling, where I'm getting very similar findings. And then the other thing we found is, like I showed you on the English to Siswati translation, is our model does particularly well on extremely low resource languages like Siswati, and also low resource tasks. So if you have, for example, a text generation task for isiXhosa that has very few training examples, that's also where our model kind of achieves the largest gains over standard subword tokenization methods. And then I've also shown you how our model, without actually being explicitly guided or explicitly supervised to do so, gains morphological knowledge during training. So it's kind of learning to some extent where morphological boundaries should be placed. We also had some other experiments where we've shown that it's better at kind of processing words morpho-compositionally, so combining the morphemes in a word in a compositional way to construct the meaning of the word. And this kind of linguistically accurate knowledge that it's gaining is improving its performance as well. So we think this is kind of one of the underlying reasons why it can outperform standard subword tokenization methods. But just more broadly, so if I consider kind of the findings of my PhD, within the current NLP research landscape. So there's two kind of trends that have taken over NLP in the past 10 years or so. The first is this tendency towards learning everything end to end. So you don't add additional linguistic information anymore if you have enough data. You just let the model learn everything by itself in an end-to-end fashion. So you just give it the output, give it the expected output, and it basically learns all the steps in between independently. The one kind of aspect of the NLP pipeline that has not been included in this end-to-end kind of paradigm is subword tokenization. So we think that in cases where subword tokenization is especially important, like the Nguni languages and low resource settings, subword segmentation is important enough that it can also benefit from being included in this end-to-end pipeline. Okay, it can also be something that the model actually learns to optimize for the task as opposed to a pre-processing step. And the second trend has been this idea of just applying the same neural network architectures to all languages. So nowadays it's a transformer model that's just applied universally across all languages without any modification. And you have even the more extreme example of models becoming more and more multilingual, so having not just the same modeling technique for all languages, but actually having one model that is responsible for hundreds of languages at the same time. And this actually we think is not always the best way to go. So I think that you know our work has shown that if you can kind of give the model some kind of some bias or some inductive bias in its modeling that is specific to languages. So, for example, targeting the linguistic characteristics of certain languages, this can still be beneficial for performance. I don't think we're at a stage yet where kind of all or the same neural techniques can be applied to all languages, especially with regards to languages that just don't have that much data available. Then it's still useful to have these linguistic biases. So in general, in deep learning for low resource NLP, there's kind of a few approaches that have emerged. Like I said, so firstly, it's just actually for creating datasets, which is still one of the most important things to do for these languages, to actually improve performance and also understand or improve our understanding of how these models are working on these languages. Then to actually just improve performance, multilingual modeling has kind of emerged as the most important, the most successful method. And then also another technique is data augmentation. So where you kind of try and get the most out of the data that you have by either synthetically generating more data or training your model in a specific way that it kind of gets the most out of the data. So a lot of these techniques, they just basically try to take what's worked for high resource languages, which is basically scaling deep learning and training it on more data and making the models bigger and applying that to low resource languages. While our work I would describe as linguistically informed neural modeling. So we're still using deep learning techniques, but we're trying to kind of equip these models with knowledge or with biases that are linguistically informed, so that we can build models that target specific attributes of these languages. In our case, it was kind of building subword-driven models to target the agglutinative morphology of the Nguni languages. And I think this approach is an interesting thing to work on, and also a promising approach for other low resource languages as well. So that concludes my talk. Thank you very much for listening. And if you're interested in more of this work, then you can visit our group's website or my website to see some of the publications that I've spoken about in this talk, but also some other stuff that we've been working on. For for example, on easy-cause-out data to text generation. And yeah, we also have some more work on kind of trying to design linguistically informed models that still use the deep learning approach, but for specific low resource languages. Thank you very much.
Great, thank you. That was a very, very interesting presentation. And I see it's not just me who found it interesting. There are quite a few questions in the chat as well. And some of them are quite related to a few that I wrote down. So let's go through them. Okay, so Wouter Klopwijk asks, on average, how many tokens per English word versus per Nguni word? So 1.3, 1.5 tokens per word. I think this is just the subword tokens.
So let me actually see this. So is this reference to a specific tokenizer, or so I can maybe just say, so in the what they found in for example, commonly used applications, so for example ChatGPT, or if you just use a standard Subword tokenizer, is that there will be many more tokens per word for low resource languages like the Nguni languages, and many fewer words many fewer tokens per word for the English language. And this is because it's frequency based. Okay, so if your data set is largely English content, then the English words will just have a higher frequency, and so they'll kind of be overrepresented in the subword vocabulary, and your lower resource languages will be underrepresented in the subword vocabulary, so there will be many more tokens per words. Something that we found in our research is that there's sometimes still an over tendency with our models to revert to like a character by character tokenization. So if it's not seen the word before, then sometimes it'll just go to kind of character by character, which is not ideal necessarily, but that's just what happens when you let the models learn from the data.
Okay, so I hope that answers that question. Tanya also has a few questions. How computationally expensive is it to keep all options for subwords open? And I think that's almost the approach that you've taken, right? And then learn the identification. So isiZulu can have very long words, hence the question.
Yes. So so a big part of my our work on this is basically trying to get this computationally more efficient. So we do have to actually go through all the possible combinations of subword tokenization. We have a dynamic program that does that. It can compute that much more efficiently than just doing it by brute force. But we also have certain kind of limitation or assumptions that we encode for computational efficiency. For example, you can limit the maximum length of a subword. So you can say, okay, the subword can't be longer than 5 characters, which is not going to always result in accurate subwords, but it's kind of a necessary approximation for computational efficiency. And then, yes, so for the second question with the English to Swati performance, yes, our models does better on when trained on the smaller Siswati dataset than the other baselines. In terms of other low resource languages, so we've tested it only on the Nguni languages, a few other South African languages, some of which are also low resource, and we've tested it on Finnish as well for a few tasks, since that's also agglutinative. We found that in general, it doesn't always work for low resource languages. It works if the languages are both low resource and agglutinative. So it has to be the combination of those two. And then I see there's a question about a repository for native language NLU datasets. So I mean the Satilar website is what I usually use for that. But for the internship that I did, I collected a bunch of datasets, or just to kind of run models on all of them, and I've collected that on a GitHub page, which you can find here if you want to scan the QR code. But a lot of these are just cellular datasets as well.
There's another question by Kale.
Question?
I actually had a few questions related to that as well, but I think his question actually nicely summarizes it.
Yes, so this is
Subword segmentation close to morphemes, yeah.
Yeah, so that's actually something we definitely want to still investigate a bit more, because we've had some interesting findings there. So we did try for some of our machine translation work to basically just segment the words into morphemes using supervised morphological segmenters before you apply something like BPE or Subword tokenization. So then there's no way for the tokenizers won't ever cross morpheme boundaries, but that either led to worse performance or didn't improve performance. So I think so. Kyle said that if there is a sweet spot in the middle between subwords. So I think there is a sweet spot somewhere between morphemes and having some morphological information, but not so much that you kind of limit your model to learn subwords that are good for the task. So, some morphemes might be useful for the task, but in other cases, it might actually be useful to either maybe represent two morphemes as one subword token if it occurs so frequently, or to maybe rare morphemes to instead represent them as characters, perhaps, or yeah. So we have tried using morphemes themselves, and we haven't found good performance with that. But there's been some interesting work by other researchers, basically trying to create like a version of BPE that kind of incorporates morphological information, and that actually worked quite well. Like if you Google BPE knockout, that is something that that seemed to work well. So that kind of, I think, found a sweet spot between the two.
Yeah, I was wondering there as well, and I see Friedel now mentioned at the bottom a reference to Morphessor. I mean, there are a number of unsupervised morphology learning systems. I was wondering how that would work, but I think you've kind of answered that as well. Or take a completely different approach, something like a minimum description length, where you try to minimize the model. I'm not sure if these things have been tried, or if it doesn't work because you need to have this kind of in between small and big chunks.
Yes, so we did actually compare to Morphessor on not in the machine translation work, but in our language modeling work. And our models did better as unsupervised segmenters than Morphessor. Especially if, so we had in the language modeling, we basically tried to see, okay, let's forget about language modeling, but let's just see how good these models can be as unsupervised segmenters. So for that, we just trained them on like one word at a time. And then our models did very well as unsupervised morphological segmenters. So I think it's actually it can be used for purely that as well. And someone asked if we're planning to put together data sets ourselves. So we haven't done that except for a data to text data set. So this one mentioned over here, T2X, is something my supervisor Jan worked with some researchers at UWC to put together, and we released that in a part of a paper that we published this year. So it's a isiXhosa data to text dataset, which is one way that you can test kind of if the models can generate isiXhosa text that's kind of coherent and still and encodes the meaning of the data. So you'll probably find that if you I don't know, Google, go to my website and find the link to that data set. I think it will be there.
We're running a little bit out of time. I know people will have to leave at some point. There is still a few small questions left, perhaps. We can tackle these.
No, I can't speak any of the Nguni languages besides like taking very basic introduction to isiXhosa classes. But we do have isiXhosa speakers in our research group who can help with some of the kind of checking some of the model output. We also, when we developed the data set, obviously there we worked with isiXhosa students. But yeah, a lot of our work is still data driven. So we do depend on kind of the quality of the data for example, large scale evaluation, which is not ideal. It would be better to have more more scaled kind of human evaluation of some of this work. But that obviously is challenging to do, but something we definitely want to do.
I see there's one question left. I don't think you covered that on the spelling variation, whether that affects modeling.
Variation spelling. Yes, so that absolutely complicates the modeling process, but so that's kind of depends on if those variations are represented in the data or not. And if your data is small, then it probably won't be represented to the degree that you want it to, so the model won't be able to generalize. But I mean, that is something that Subword tokenization, that's one of the reasons people use Subword tokenization. So that kind of small spelling variations won't affect the model's understanding of the entire word. But yeah, I mean, that's unfortunately with our approaches, it kind of depends on if it's represented in the data or not, and to what extent. But I will say, I think our model, so the fact that it generalizes better to kind of new combinations of morphemes, I think will mean that it can kind of handle some of these other variations a bit better as well. It just kind of generalizes better to variations in subword spelling and combinations as well.
Yeah, wonderful. Thank you so much. I think we've covered all the questions at this moment. I don't see anything new. No, so thank you again, Francois, for the presentation. I really, really appreciate it. And I think a lot of people, seeing the number of questions, really liked it as well. So thank you so much.
Yeah, thanks everyone for coming. It was great to talk to you today. Thank you.
Cool. Thanks. Bye-bye.
Bye-bye.